Today we're going to be talking about the heading indicator, with its members being apelado, manganar, paras, and so. In this episode, you will tackle the following: overview, history, operation, development, applications, and regulations. First, we have the overview. The overview of the heading indicator. The heading indicator is a flight instrument used in an aircraft to inform the pilot of the aircraft's landing. It is sometimes referred to by its older names, the directional gyro. The primary means of establishing the heading in most small aircrafts is the magnetic compass, which, however, suffers from several types of errors, including the created by the dip, or downward slope of the Earth's magnetic field. Dip error causes the magnetic compass to read incorrectly whenever the aircraft is in a bank or during acceleration or deceleration, making it difficult to use in any flight condition other than accelerated, perfectly straight and level. To remedy this, the pilot will typically maneuver the airplane with reference to the heading indicator, as the gyroscopic heading indicator is unaffected by the dip and acceleration errors. Next, we have the history. The history of the heading indicator. Early pilots simply made use of borrowed land and sea navigational compasses in their cockpits. However, liquid-filled compasses were not perfect instruments. Steep turning and diving maneuvers caused the compass to present inaccurate heading information. In addition, metallic objects in the aircraft created magnetic interference that could corrupt the compass heading display. Some pilots made use of small magnets of opposite polarity positioned near the compass to counteract this harmful interference. Another solution for overcoming the interference was provided by the compass correction card, and it is still in use today. Early indicators were of two types: mechanical and differential. Some mechanical devices were very simple, producing only limited information, much like the mechanical stall warning indicators in use today on small private aircrafts. Other mechanical airspeed indicators grew to be quite elaborate. The early pilot's only tools for estimating his height above the ground was his eye. He made use of the eye's ability to detect changes in the size of the objects as he flew to estimate his altitude. In addition, the eye's capability for detecting subtle changes in the texture of the landscape below provided him with altitude clues. Also, the eye's interest binocular nature afforded him a certain depth of degree with perception. Next, we have the operation. The operation of the heading indicator. The heading indicator works using a gyroscope tied by an erection mechanism to the aircraft yawing. Example: the plane defined by the longitudinal and the transverse axis of the aircraft. As such, any configurations of the aircraft yawing plane that does not match the local Earth horizontal results in an indication error. The heading indicator is arranged such that the gyro axis is used to drive the display, which consists of a circular compass card calibrated in degrees. The gyroscope is spun either electrically or using filtered airflow from a suction pump driven from the aircraft's engine. As the Earth rotates, and because of small accumulated errors caused by the imperfect balancing of the gyro, the heading indicator will drift over time. and must be reset using a magnetic compass periodically. The apparent drift is predicted by a sin latitude and will thus be greatest over the poles. To counter for the effect of the Earth rate drift, a latitude knot can be set which induces a real wander in the gyroscope. Otherwise, it would be necessary to manually realign the direction indicator once each to 10 to 15 minutes during routine in-flight checks. The operation of the heading indicator depends upon the principle of rigidity in space. The rotor turns in a vertical plane and fixed to the rotor is a compass card. Since the rotor remains rigid in space, the points of the card hold the same position in space relative to the vertical plane of the gyro. The aircraft actually rotates around the rotating gyro, not the other way around. As the instrument case and the aircraft revolve around the vertical axis of the gyro, the card provides clear and accurate heading information. Because of precession caused by friction, the heading indicator creeps or drifts from its set position. Among other factors, the amount of drift depends largely upon the condition of the instrument. If the bearings are worn, dirty, or improperly lubricated, the drift may be excessive. Another error in the heading indicator is caused by the fact that the instrument gyro is oriented in space, and the Earth rotates in space at a rate of 15 degrees in 1 hour. Thus, discounting precession caused by friction, the heading indicator may indicate as much as 15 degrees of error per every hour of operation. Next, we have the development. The development of the heading indicator in terms of its timeline. So for the first, we have the analog instrument. It is a mechanical instrument designed to facilitate the use of the magnetic compass. Second, we have the remote heading indicators. Remote indicating compasses were developed to compensate for the errors and limitations of the older type of heading indicators. And lastly, we have the Attitude and Heading References Systems, or AHRS. Electronic flight displays have replaced free-spinning gyros with solid-state laser systems that are capable of flight at any attitude without tumbling. Here we will be discussing each term. Original analog flight instruments are operated by air pressure and the use of gyroscopes. This avoids the use of electricity, which could put the pilot in a dangerous situation if the aircraft lost electrical power. Some heading indicators, referred to as horizontal situation indicators or HSI, receive a magnetic north reference from a magnetic slaving transmitter and generally need no adjustment. The magnetic slaving transmitter is called a magnetometer. Development of sensing and display techniques combined with advanced aircraft electrical systems has made it possible for reliable primary and secondary instrument systems that are electrically operated. The AHRS sends attitude information to the primary flight display in order to generate the pitch and bank information of the attitude indicator. The heading information is derived from a magnetometer that senses the Earth's lines of magnetic flux. This information is then processed and sent out to the primary flight display to generate the heading display. Next, we have the applications. The applications of a heading indicator. The main application of a heading indicator is to guide the aircraft in a suitable or accurate direction as per the instructions of the pilots, or to the pilots. Lastly, we have the regulations. The regulations of a heading indicator. We have instrument check. As the gyro spools up, make sure there are no abnormal sounds. While taxiing, the instrument should indicate turns in the correct direction, and precession should be normal. At idle power settings, the gyroscopic instruments using the vacuum system might not be up to operating speeds, and precession might occur more rapidly than during flight. Next up, you'll be showcasing short video summary courtesy of ERAU Special VFR.
The heading indicator senses the airplane's movements and displays heading based on 360-degree azimuth in 5-degree increments. The tick marks are labeled every 30 degrees with the final 0 emitted. For example, the number 6 indicates a heading of 60 degrees while 21 indicates a heading of 210 degrees. The heading indicator does not have any built-in heading sensing ability, so at the start of every flight, after the engine is running, the pilot must realign the instrument to correct heading, referencing the aircraft's magnetic compass. To accomplish this, trigger a push-in the knob on the lower left side of the instrument. This both disconnects the gyro from the compass card and aligns the gears of the knob with the gears connected to the compass card. When you complete release the knob, the driver will reconnect to the compass card. Unlike the attitude indicator, the heading indicator is oriented so that only the horizontal axis is used to drive the display. When the aircraft turns, the gyro and attached main drive gear remain in their orientation that causes the main drive gear to rotate the compass card, which then rotates the compass card on the face of the instrument. Due to friction and precession, the heading indicator may slowly drift away from the correct heading, and because of this, the pilot should double-check the accuracy of the instrument against the magnetic compass and realign as if necessary. This should be done roughly every 15 minutes.
These are the references used in this video. Thank you for watching and see you guys in our next episode.